Hello everybody, my name is Barsha and we are talking about GPU versus CPU or CUDA C++ versus C++. We comparing traditional calculation which is done by CPU and C++ versus um, a calculation done by CUDA C++ and GPU, and we're comparing the results of these processes. So if you want to skip, I will mark in the comments, I will mark the CUDA C++ part, and if you want to skip C++, which you already know, then you can go on part where you hearing about CUDA C++. And now let's begin with today's theme or today's topic. Today's topic is multiplication of the matrices. We usually know how conventionally it is done. Well, the size of the matrices we took 64 times 64, and that makes total, I think, 4096 elements, and we must multiply them first in conventional way via C++, and then we will go CUDA. First of all, let's introduce ourselves, like famous introduction always. When we begin, standard IO stream to output the results and so on. We are using vectors for easier work with the arrays, or for this matter matrices, because um, uh, matrices can be represented as arrays of arrays. So this will be probably arrays of arrays, which consist of 64 elements, and we have 64 that kind of elements. But we will see that in the process. First, let's start with the main program. We just here make the constants. We also have measuring time, and everything here is as usual. So let's go with the main thing, and that the main thing is main program. Of course, we have formation uh, of the matrices. This is matrix A, as you can see, and first we inside of it we define or make the array, and we have n number of these arrays of arrays which are filled with ones. So this is a kind of way to form the columns and rows. One row is this one, and we have and that rows. So let's go further. Also, we're doing that for the matrix B. We putting one in one array of n elements, all filled with ones, and then we form the n that integer arrays. You see how it's done. Probably there is other ways to do it, but they suggested to use this. Probably it is much more efficient or so on, maybe. But it's not main topic. This is very well known and usual thing in C++, so no need to go with more details than it's necessary for this process, in which we are actually doing different thing, and that's the comparing of the speeds of the CPU and GPU for 64 times 64 elements. Also, we're making the result matrix, which will be filled with zeros to avoid yeah, we have blanco result matrix where we can put results. So we can go further. So we define the space in RAM memory, and how it's filled inside the RAM CPU or system RAM memory. Then we are starting with measuring the time. This is a familiar thing which we met many times before. High resolution clock, we use, let's say, method high resolution clock from standard chrono heading. So nothing new now. Actually, now is method for this matter. And then after we start the measuring the time, we start matrix multiplication. We of course have I, which is going from 0 to n. Also j, which is coming from also 0 to n. You know standard format that we go by the rows and for A and columns for the B. So we're going by the rows for A and columns, column elements for the B matrix, and then we multiply for each element of A. We doing that. Also, we multiply each element of column of row A and each element of row B, and we putting the sum in front as a 0, and then we doing this actually this for loop. Third for loop is for the multiplying of elements of rows and elements of columns. And for each of them, when we go with the k through them, we multiply all these elements with the same index you see here. And this is element number inside the row, and this is element number inside the column. This is basic stuff for matrix multiplication, so we expect to know that, as they say on the colleges and faculties. We expect you to know that. And when we multiply these two elements, we adding to this sum, and this sum represents actually one element which is created in a result matrix, which represents multiplication of elements of row I and elements of column J, and all these elements which are multiplied then and added to the total sum for this process, they are stored inside one element, this sum. And then with every new iteration, when this first this for loop is executed, and then we going back to all other for loops, and then going to the next row, next column, or for one I, we took all these columns, then for increment the I, and then go through all these columns again, and so on and so on. This is a standard way for the matrix multiplication. No need to go through the high school algebra, but maybe it will be done. If this stuff is not clear, you can say it in the comments. We can repeat or not repeat these chapters of the algebra. And then when we finish the multiplying of all columns, of all rows and columns, we have the result stored in all all these n times n result matrix, which is C, and these are how we gain this each elements, how we make it. After the finishing the process of multiplication of two matrices, We can stop our time, measuring our time, define new moment, and put it in this new variable end. Previous one was start, as you can see. And then we can make or calculate duration with this function, which is coming from the chrono method, duration cast. And here is given in microseconds. Previously, it was given in nanoseconds. And we from end we subtract start, and then we have result. And then we form the variable in microseconds, which we put in the duration. It will be described as duration. For the probe and testing of good executed process, here is given to write down on the screen first element of that matrix and last element of that matrix, as you can see. And then executed time is the duration. We want to write down the execution time for this process of multiplication inside on the screen. Yes. There is a good science which speaking about polynomial or not polynomial processes, and it tells you of order of magnitude of execution, and we have here four loops here, of four loops here, and it will be one inside of each other, and I think the order of magnitude is n times n times n, if I remember correctly, but this is not important. Let's execute this C++ program and see how it's going. What is this? Some strange things is happening. Oh. Let's turn down this silly yeah, we can stay with this. We want to add PowerShell, and then we can go with compiling and making executable program. Okay, we are not executing but compiling. Come on, buddy, what takes you so long? And then we will do the executing of the program and see the results. Okay, yeah, there the process is done correctly, because when you multiply 1 and 1 and add it to next, which is multiply 1 and 1, you have 64. Also, first and last, they are the same, and we have the results here: 3,133 microseconds execution time for execution time for CPU single core. Okay. We see that this multiplication takes more time than adding to, for example, arrays of 3072 elements. Let's execute this program one more time. Okay, it's a little bit bigger, 4076. Nice. Yeah, it varies probably because of preoccupying of the course and finding core for the execution. We didn't speak here about the multi-core process, but for the bigger number of elements, Copilot promised me that it will be more efficient for millions and 10 millions of elements. It will be more, let's say, efficient to do the multi-core or parallel processing of these tasks, and we will do it. And also we will do it in beside C++, we will do it in Go program. But enough talk. Okay, let's go to the CUDA program execution and to see how it's done. We see here order of magnitude of microseconds, how much does it takes. We expect for this small number of elements that CUDA is still not efficient as classical C++ on a single core, because that core is more bigger and efficient than classical CUDA cores for execution. But what we have here, okay, we have established some constant integer 64, and now of course we have CUDA kernel or kernel or function which will be executed on the GPU. The name of that function is mat multiply kernel. We inputting A and B, of course, classical story, and the result is C, and we are expecting here integer for the number of the elements. Then what we got here? We have, as we usually say, for the CUDA course, we don't have a classical variable, integer variable, which goes through the um, for loop. But here we establishing some processes which for row and column for these variables, for these counting variables, which are self-assigned and in some range which is given inside the call of this kernel function, and every parallel process is given one or automatically given one index for this. And how we know it? No, because we are calling here some values which are connected with that. Okay, what is happening here? We have one row, and we want to go through the indexes of one row and of row index. Sorry, and we have here thread idx dot epsilon. This is defining one thread, for example, and this variable will bring one index value which will be stored somewhere, and the incrementation of the threads will be there. Also, Copilot suggested that we take here that we separate all those so many threads to separate them inside the blocks. So we have one number of blocks which are going through the or to the block, and so block dimension is how many threads we have inside how many threads do we have inside one block. Okay, we have here, as you can see, this is dimension is epsilon. Because we are forming the index, and I don't have representation here, but we are forming indexes for the indexing row. We actually we going one row, second row, third row. We are going through dimension epsilon. So that's why here we see epsilon. But this is just to say that a regular dimension for the row is x. It's hard to explain, but we will make some visual video to have support for this. Of course, this is telling us that this will be executed on a CUDA course. So dimension X, we are separated inside the blocks, which going one by one. We are picking all indexes inside the blocks. We picking up all indexes for the rows. Also, we are picking all indexes for the columns, and this, when we use these variables, or how to call it, program knows that we are picking up and making parallel different indexes or set of indexes for the parallel execution. And of course, which is strange always, is to go from the for loop to this parallel. And this is most confusing part for the beginners in the CUDA programming. But when time comes, you need to learn it, and we will try to learn it on a good and proper way. I am thinking to make one visual video which will support this and explain in much more details. And now we have also this is the limitation. How far do we go inside inside the process of these indexes or indexing? As long as we lower than n, which we input here, and lower than n with row index and column index, and together, as long as we under this or beneath this n, and this value will come in kernel calling, will come and go inside this value. As long as we are under this value at the same time, and for the row index and for the column index, which is separate, which is corresponding to, in previous case, to index I and index j, and this column and row. So what we have here as a row or column index, here a similar thing was I and j, just to make some reference. What is it? Then we are, let's say, setting sum to the 0, and we are going through the k column, which will help us to sum all these elements for the fixed row value and fixed column value, because we are making the sets out of this for each row and column. We're making the sets of threads which will be executed. So for that one particular index row and particular index column, you are going through the k and taking the element row times n plus k. This is standard indexing, because this, as you remember, and to make it parallel, this represents that index I, and this is going through the k. This is going through the specific element. You can find this inside basics of any kind of programming in matrix multiplication, but imagine that similar process and indexing is actually happening here. So this is one row, a current index row. For that, let's say, copy of execution, a copy of function of execution for exact index row and for exact column index. And also here we have and we're going through the all elements like in previous case. Here we go through, we pick up, let's say, one I and one j, and inside we multiply through the k, which is going from 0 to n. We multiply all these n elements all these n elements of that row and that column. So similar here. This is representing, let's say, I, and this is representing J index. And this is standard address finding, but not in conventional way, but let's say in computer way. And because we are storing this, and this is also not traditional, let's say, indexing, but that addressing arithmetic. We go and assign for that specific element, we assign that complete sum as a value to this one. So this is corresponding here to this one. We are forming exact one element, but this is more like arrays of values, which is going row by row, or in memory. Vectors or matrices particularly are going one by one inside. So not let's not waste too much time. This is for much more explanation in detail for maybe special video with some more visuals, which can talk about this topic. But you get the analogy here. This in C++ is actually corresponding to this, but with using addressing arithmetic to go to the specific element. So this is specific element of the result matrix, and this is a CIJ in some way inside the matrix C. Okay, when we describe this kernel, we are going through the main program, and then we have here forming of sizes, and size is n times the size of integer. We are this integer value will help us to allocate the memory for in later process. So that's the purpose of this one. We are forming or assigning to this pointer, we are assigning or allocating the space, which will be new integer n times n, so it is n times square space. No, n times square is n squared space, and it will be filled with integers, and we making new also for the B matrix. We have this pointer allocating some space, and for the result matrix we allocating some space with the pointer, and we can go further. We are here initializing this A and B's with ones. I'm not sure why we didn't go here through and put the C matrix into the 0, but it's not matter. Probably because it will be decided or let's say defined somewhere later on, or do the initialization of this C matrix. This is the allocating of the space inside the GPU memory and assigning the pointers for A and B, for DA and DB pointers for matrices A and B. And we are also defining the pointer and the space. This is allocating the space with size of size, yes. With the void star star blah 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 to the result matrix, but inside the GPU memory. And we have transferring of A from A inside the CPU memory to the D of DA inside the device or GPU memory, and we have from host to device also for the matrix B is the same process from the CPU to the GPU memory and allocating the not allocating but um, delegating these elements from the CPU memory to the GPU memory. These let's say integer elements. Of course, here is written host to device. Later, when we returning the values, we use from device to the host, but we will see that later. Here we have dimensioning here dimension 3 threads per block. We defining here how many threads we have inside one block, and actually we are assigning the dimensions of the block. So block will have two dimensions. I'm not quite sure is this one x, this one epsilon, or vice versa. I think it's maybe this one is x, this one is epsilon. And then we are so total size of one block will be 16 times 16, it's 256. And let's not forget that usually the size of the block is 256, which is corresponding to one TPC, which have two streaming multiprocessor. And one streaming multiprocessor have 128 CUDA cores. So two streaming multiprocessors will have 256 CUDA cores. So this is corresponding to two streaming multiprocessors for the execution in parallel, because we have 256 CUDA cores for execution. And then we defining the number of the blocks, we must see how these 60 how does these blocks are fitting inside this taking the or reserving the total space, not total space, but how these blocks, how many blocks do we need for 64 times 64 elements. And you will see probably when you go through this process, you will have probably 4 by 4. We will have 4 times 4 blocks, which corresponds to 16 blocks. I'm assuming this is 16 blocks. We can maybe in next video we can print here how many blocks do we have. And then we defining the variables start and stop, and we allocating some pointers to or addresses. Could event create? We have some maybe addresses or pointers where this will be time will be stored when start counting. And we have here a start of the recording. We're recording this time. Then we are calling the kernel. So threads per block, what do we have here? We define threads per block. 16 times 16. We have two dimensions, x and epsilon. I'm not sure is this x or this is epsilon, but there is one video which is, but it's on Serbian, which is talking about this. And this is the we have 16 times 16 times 16, which is 256, as a number of threads inside one block, and the number of blocks is defined here with these two values which are defined, which we define these dimensions x and epsilon as 16 and 16, no matter what order is in discussion. And yes, we add total number of elements. No, n elements. N elements is 64. We have 16 here, and blah blah blah. We will discuss this later. It's not so important for this topic. So we have threads per block, which is 16 times 16. This is that dimension, and we have in one dimension it's 16, and in another dimension it's 16, but total number of threads for one block, and this is how the block is defined. And we have here 256, and we have number of blocks calculated through this process. Let me check. Yes, we have, so this is one dimensional block. So we have probably 16 here. This is another dimension of block. Yes, so this is x, this is epsilon for the number of threads per block. And this is how many blocks we have for x and for epsilon. So this is number of blocks of per x dimension, and this is number of blocks for epsilon dimension. Okay, everything is clear here. So this number will be, I think, 4, and here we'll have, I think, also 4. So here will be, so 4 here and 4 here, and 4 times 4 is 16. So here should be 16, and here should be 256. And if you multiply, let's say 16 times 256, let's calculate this. The total number of threads should be as the number of elements. So let's say 64 times 64, that's the number of elements, is 4096. And if we multiply 16 with 256, we have the same number. So yes, we cover with this. Here is number is 16. Here is 256. When you multiply these two numbers, you have 4096, which is corresponding to the total number of elements of matrix A and matrix B and matrix C, which is the result matrix in this case. Here, of course, n as is defined, it's 64, and we stopping stop time. We stopping, yeah. We stopping this CUDA event record. Yes, we marking this event and put it in stop, and we have CUDA event synchronize. Also put it in stop. Stop value float, we defining the milliseconds here. It is measured in milliseconds, and we calculating elapsed time and storing it in milliseconds. Then we transferring from the data from the result data from the GPU memory to the CPU memory. As you can see, from device to the host, this is standard procedure. Printing one element on the beginning of the matrix, last element. You can see here this matrix arithmetics. And time measured in milliseconds is here, so we will see what is happening with this and compare it to the C++ time. and we are deleting these these memories or allocations on the CPU RAM, and we freeing this memory allocated to the GPU RAM or on GPU RAM, and we return 0. Let's go to the execution. Okay, we saw everything we need to see. What's happening? Okay, shut up. CUDA 4. Yeah, let's do some MVCC is calling for the compiling of this, and this is for the linking, blah blah blah, using CCBin G++. Let's compile this program. Okay, let's execute this program in VSL. Nice. Okay, what we have here, it's 64, so checking is okay, as we expected. And here is time in milliseconds, which, okay, let's check this. No. Let's check in PowerShell. Here, yeah, microseconds. This means that this is 3 times 3.170 milliseconds, the execution time. So here, let's say, let's round it to the 3 milliseconds. But here we have 1.5 seconds, milliseconds. So here in PowerShell or C++, it is 3.1 or 3.2 almost, and here it's 1.6. So for this matter, it seems that this program is executed faster. Let's execute it one more time. Wow, nice, less than 1 millisecond, so it's still faster. When we 64, we can say that when I did this for the probing and testing yesterday, I think CPU was faster, but actually it seems that for this matter is even GPU is faster, but this is without transferring time from the GPU memory to CPU memory. We didn't take that stuff into account. We just taking into account of this calculation or multiplication and execution time. So yeah, in total here we have 496 elements, but because we are multiplying and taking all the rows, it's much. We are taking into account much bigger elements, much process of the gaining the one value for the element of the matrix C. The process is much more complicated than adding two matrices, not matrices, but even matrices and two arrays. So that's why probably GPU is a little faster. And also, let's check one thing. We can maybe go in further executions and times. Let's see the occupying. How much this is affecting a GPU in percentage. So let's go performance. Yes. Okay, buddy. Let's see how you're performing. Wi-Fi, GPU, yeah, blah 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 blah. This is integrated and this is NVIDIA. Okay, let's go with this body. Uh, and let's execute the program. Okay, where are you? What's... Ah, there you are. What's happening with this K? Okay. Okay. Oh. Video encode. 3D. Let's see some parameters. Percentage. What happened with the memory? This is the GPU memory. This is shared memory. Okay, let's execute it one more time. It just told me that it just told me that 3D is jumping, but video encode, video decode, copy. Okay, let's see what's happening there. This is small amount of elements, so it doesn't affect occupation of the GPU memory, but we will do the harder test with much more elements. But let's see another one more time. Okay, there is only peak probably because of the preoccupying of the without okay with preoccupying the CUDA cores. So I'm assuming that this jump is from there. So nothing particular. Okay, let's stop with this. Too much spreading the story. We saw the main things, and we will enlarge the number of elements which we are dealing with. So let's go to some millions and see the behavior in that case. But this is good for the beginning, and the matrix multiplication on the single CPU core and matrix multiplication on the multiple CUDA cores and other things done on GPU, done on RTX 4060 laptop version. So we will see the performances and make some conclusions and see how to separate logic which should be done on as algebraic tasks and which cores we are using for the operating system tasks and all that stuff. Okay, we are stopping here and see you later, alligators.